Hey there, and welcome to this explainer. Have you ever stopped to wonder just how a computer processes incredibly complex mathematical equations in literally a fraction of a millisecond? It's super tempting to picture this chaotic labyrinth of logic boards and tangled wires. But honestly, the truth is, computers handle these dizzying tasks using a surprisingly simple, almost elegantly straightforward organizational concept. Today we're going to explore Chapter 26, Appendix E of our source material, and we're breaking down this magical hardware structure known simply as the stack.
Here is our quick roadmap for today. We'll start with Section 1, what is a stack? Then hit Section 2, inside the machine's memory. Next is Section 3, the power of postfix. And finally, Section 4, stacks in action.
Okay, let's dive into this. Section 1. What exactly is a stack? Let's talk about the LIFO principle.
At its absolute core, a stack is just an ordered set of elements where you can only access one item at a time. The absolutely crucial point here is that items can only be added to or deleted from the very top. This creates what we call a last-in, first-out list, or LIFO for short. You might also hear it called a push-down list. Think of it exactly like a physical stack of dinner plates at a buffet, or maybe a massive stack of papers on your desk. You don't just yank a plate from the very bottom. That would be a disaster, right? You take the one that was most recently placed right on top.
So because we can only ever interact with the top of the stack, the rules are incredibly streamlined. A push operation literally just appends a brand new item right to the top. A pop operation deletes that top item. We also have unary operations, which perform an action on just that single top element. And then there are binary operations, which need two operands, like when you're adding or multiplying. For a binary operation, the computer will literally pop the top two items off, do the math, and then push the resulting answer right back onto the top of the stack. It's that simple.
Let's actually visualize this concept in motion. The stack pointer, which is usually labeled SP, acts kind of like a bookmark. In its initial state, let's say it's pointing to the letter J. When we push the letter I onto the stack, the pointer physically moves up to track it as the new top. When we pop I right back off, the pointer drops back down to J. Now consider a multiply operation. It pops off both J and K, multiplies them together, and then pushes the new result J times K onto the stack, with the pointer tracking that brand new single result. So it's incredibly dynamic, but strictly ordered.
All right, moving on to Section 2, inside the machine's memory, looking under the hood.
So physically, a contiguous block of locations is reserved inside the computer's main memory specifically for this stack. Most of the time, this block is only partially full. It's neatly divided into an in-use space down at the bottom and a free space at the top. This gives the stack plenty of room to grow dynamically as new items are pushed onto it. Now, to keep this whole system from just totally crashing, the processor relies on three critical addresses, which are usually stored right in the processor registers. First, we have our stack pointer, which, as we know, tracks the exact top of the stack. Second is the stack base. This marks the absolute bottom. If the computer tries to pop an item when the stack is totally empty, hitting that base triggers an error. Finally, there's the stack limit. This marks the far end of the reserved block. If the computer tries to push a new item when the block is completely full, boom, it hits the limit and triggers a stack overflow error. These three addresses essentially act as the guardrails for the entire memory block.
The stacks also have a physical direction they grow in within the memory. An ascending stack grows towards numerically higher memory addresses, but, and this is super fascinating to discover, a descending stack, which actually grows towards numerically lower addresses, is often the default implementation for most machines. That includes the entire x86 architecture. It seems totally counterintuitive at first to grow down into lower numbers, but it works flawlessly.
There's also a weird quirk in how we talk about stacks that our source points out. You'll often hear the terms full and empty methods. Now, actually, scratch that, it's a bit of misleading terminology. It definitely doesn't mean the stack's capacity is full or empty. Instead, it just dictates exactly where that stack pointer rests. In a full method, the pointer rests exactly on the top item. But in an empty method, the pointer hovers over the next available free space right above the top item. It's basically just a difference in how the machine prefers to track its boundary.
Section 3, the power of postfix, a new way to math. Now, what's really interesting about this slide is how it totally shifts gears.
Think about it. How does a computer efficiently solve complex math? Human math is, well, it's incredibly messy. We write formulas with the operators stuck right in the middle of the numbers, like A plus B. And for complex equations, we use layers upon layers of parentheses to dictate the order of operations, plus we have implied rules where multiplication takes precedence over addition. For a computer, constantly scanning back and forth to parse all these human rules is an absolute nightmare.
So computer scientists use an awesome alternative, postfix notation, which is also known as reverse Polish notation. Instead of putting the operator in the middle, it goes at the very end. So A plus B becomes A, B plus. And here is the absolute aha moment from the text. Regardless of how insanely complex an expression gets, postfix entirely eliminates the need for parentheses. No implied precedence, no nested brackets, just pure left-to-right logic. And why is eliminating parentheses such a game changer? Because an equation in postfix format can be flawlessly executed by, you guessed it, a simple stack.
Which brings us perfectly to Section 4, Stacks in Action, the Algorithm at Work.
When a computer reads a postfix expression, it follows 3 beautifully simple rules. Step 1, scan the expression strictly from left to right. Step 2, if you see a variable or a number, boom, push it onto the stack. Step 3, if you see an operator, like a plus or a multiply sign, you pop the top 2 items off the stack, perform the operation on them, and push the result right back on. Once you've finished scanning the whole line, your final, fully calculated answer is just sitting right there, all alone at the top of the stack.
Let's speed things up a bit and actually watch the machine crunch a complex equation. First we push A, then B. Oh, we hit a minus sign, so we quickly pop B and A, subtract them, and push A minus B back on. Next we push C, then D, then E. Boom, a multiply sign. We pop E and D, multiply them, push the result. A plus sign. Pop that result and C, add them, push the result. Finally, we hit a divide sign. We pop our 2 massive remaining chunks, divide them, and push the final answer. The computer never once had to jump around or decode tricky parentheses. It just marched straight through, relentlessly pushing and popping.
But wait, humans definitely don't type in postfix. We type in normal, messy math. So how does the computer convert it in the first place? Well, many compilers use a brilliant algorithm designed by Dijkstra, and incredibly, this algorithm uses a stack to do the translating. It scans our human math from left to right, outputting the variables directly, but it uses the stack to temporarily hold on to the operators and parentheses. It pushes and pops them based on their priority rules until they are ready to be placed in perfect postfix order. As you watch this step-by-step conversion, you see the tangled input being seamlessly processed. By using the stack to basically park the operators based on their priority, the algorithm effortlessly spits out a clean, completely parenthesis-free postfix output. It naturally, almost magically, reorders the equation into something the machine can instantly evaluate.
And this brilliantly illustrates why we go through all this effort. When we compare the metrics, the stack method uses what we call zero-address instructions. Because every single operation happens implicitly at the exact top of the stack, the computer doesn't even need to be told where in the memory to look for the operands. It just automatically knows. While a general register approach might seem to have fewer literal instructions on paper, the stack's implicit memory access provides a uniquely elegant and totally self-contained way to generate machine code directly from our high-level languages.
You know, it's truly amazing when you take a step back and look at the whole picture. This incredibly simple, last-in, first-out rule of organization takes the utterly chaotic, nested logic of human mathematics, completely untangles it, and turns it into a streamlined, high-speed assembly line for the processor. The stack proves that you don't always need super complex machinery to solve complex problems. Sometimes you literally just need a better way to organize.
Which leaves us with this final thought. If merely changing the way we store and retrieve data, just by enforcing a super simple rule of last in, first out, can absolutely revolutionize how computers process advanced math, what other incredibly complex real-world problems could we solve simply by changing the order in which we process the information? Thanks so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.